Hi all. Let me introduce first preliminary results of our joint project that launched 2 years ago. The main participants of this project are Institute of Education and Department of Computer Science of High School of Economics, Moscow, Russia. Psychologists and computer science professionals work together in this project, and it's an inspiring experience for us. My colleagues Olga and Alexei are here, and we will tell about this project jointly. First of all, I tried to outline some situational context. Our Center for Vocational Studies and Research interacts with Russian colleges that train workers and technicians for mechanical engineering, aviation, transport, construction. And directors of vocational schools usually said to me that vocational schools teach complicated technical disciplines for students who don't know simple, basic physical notions and concepts. I think that this issue is widespread in all the world, and vocational schools in Spain, Argentina, or China face a similar problem. And I'm sure that we need educational technologies that provide different learning pathways for weak students. Many speakers yesterday and Thursday mentioned personalized learning as efficient approach, and it's important to stress that we need not only different pathways, but we need bullet-free. Every instructor must be aware about student mistakes and difficulties, and instructor must support him. There are a lot of theoretical approaches that provide and that can be theoretical framework for personalized learning. I think concept of zone proximal development, established by Lev Vygotsky 90 years ago, one of the most influential theoretical framework. The main principles of this framework are every student becomes independent actor, and every learner tries to solve complicated cognitive problem, and usually students need some external help. As for instructor, he pushes, motivates, and gives some hints, recommendations, and so on, so on, so on. There are some technical requirements for electronic instructor. And first of all, we need, if we're dealing with material science, we need analyze professional domain and our instructor must be aware about domain ontology. And after that, we need a lot of scenarios, what to do with students' mistakes and how to support every student.
So, from the technological point of view, we have the very big underlying foundations, and here the main structure of our architecture of the system, and the main part from the scaffolding, maybe requirements here. It's the so-called scaffolding square, consists of 4 parts. It's the first part, pedagogical interventions activation system. It's the main part as the logic of scaffolding. Then it's the relevant material search and subsystem for the search special materials for current scaffolding actions. Then ontology query and subsystem, because all our actions based off ontologies, learning ontology and the domain ontology, and of course automate item generation system for additional tasks for the student. And for now we don't have time to provide the big understanding and deep understanding of ontology modeling, but this is a very cool and deep field. And here some small description of our specific ontology for MSc. Here you can see 2 main mathematical foundations as formal concept analysis and description logic, and the structure of ontology consisted of the basic thesaurus and 3 very specific parts: scales, some distinctions, and the main part for the automatic generation of items. It's a formal contexts, and some example of data structure of thesaurus nodes. It's a classical, and of course we have the special requirements for merging the different already consistent ontologies that we have in our database. For example, ontologies of the measures, the unit of measures, and so on. Then here's a small example, the very, very small example of our thesaurus in the table form, the special data structures for scales. There you can see the types of scales, the classical 4 types, and the special part, distinctors, for generating of specific quest items and test items. This is the example of such data structure, and this is the very small example of the formal contexts, because in the reality the specific contexts are very huge, really. And for now we are trying to produce the new items for different tasks based on the formal concept lattices and the formal concepts. It's the very deep foundation for dealing with knowledge, and our results shows that we are on the right way, and we can produce billions of items for several objects and attributes. And here the main methods of item generation. For now we implement 2 modes. The first mode is the classical generation of additional task items, and the second mode is the special scaffolding mode in the self-assessment. Because we have 3 types of scaffolding actions in module or in topic for self-assessment and summative assessment, and the grading after the module or topic, where we have the special task in form of the test with different types of items, and the students, in case of errors, takes additional tasks with objects and attributes where he can produce additional errors, because we have the special reasons to use the scaffolding procedures on the 6 levels, from the indication of the error up to special procedures to show up additional materials and additional tasks. And for now, we try to implement inter-model or inter-topic interaction and special scaffolding between the different models and measure the ontology of different topics. So the main results of the in-topic scaffolding are very promising, and we try to produce special scaffolding procedures on the next level for inter-topic interaction. Thank you.
Thank you very much. Please, any question?
Thank you.